So our next speaker is Dr. Vincent Gaudet. Dr. Gaudet's research interests focus on high-speed and energy-efficient microelectronic circuits applied to digital communication systems and signal processing. And he's particularly interested in stochastic computing systems and multi-valued logic, and also more recently, he's launched into machine learning like many of us. In 2009, he received the Petro Canada Young Innovator Award to recognize and support his work of outstanding young faculty-based research. And Professor Gaudet is a senior member of IEEE, and he's going to speak today on perspectives on machine learning in medical imaging. So it's all yours, Professor Gaudet.
Thank you so much, Peter. And just a quick note, first of all, thank you to Helen. I really enjoyed your talk. I think it spoke to so many important points of what I'm seeing in my own research. Let me just get this sharing. I don't know if my screen is sharing right now. There we go. Can you see my screen and hear me?
Yes.
Okay, fantastic. So for those of you who know me, you might wonder why I'm speaking about machine learning and medical imaging. After all, my sort of traditional area of research is in microelectronic circuits. So just to explain a little bit about my own background, I did my undergraduate degree in computer engineering in the early 1990s, and at that point, this was maybe during a previous wave of interest in AI and machine learning, and then so I took many courses as technical electives at that point. I also did some of those undergraduate and USRA type research projects at the university on genetic algorithms, so I certainly had an interest on it, but I had a sense myself in terms of my own personal interests that to become successful there had to be work in microelectronics, and that's why I decided to then go into that field, and you know, for my graduate work, and you know, since for most of my research, but I always had an interest in signal processing and their efficient implementation, and then I really just came back to machine learning quite recently as part of research collaborations. Again, some of you out there may know my spouse is a nuclear medicine physician, and so she interprets a lot of medical imaging, and she came up to me maybe 3 or 4 years ago and said, hey, machine learning, what is it? We want to be able to use it. And so we started working together on various projects, and that's what I want to talk to you a little bit about today. So I'm going to be talking mostly within the context of nuclear medicine, and even more specifically positron emission tomography, or PET. So you know, you may know if you've had your own imaging done or have had imaging done for loved ones. PET is a medical imaging modality. It's typically used for functional imaging, and it's within nuclear medicine. Basically, what you do, say, versus more of a structural type of imaging, say CT or MRI, is that you use radiopharmaceuticals. So you inject a radiopharmaceutical, and depending on what that radiopharmaceutical is, it might go to various places in the body, and then you do imaging based on that. You might be looking at accumulation of that radiopharmaceutical in various regions. You might be looking at more functional things, you know, what's being taken up, and so on. So just a few pictures here. I don't know if you can see my mouse, but on the left hand side is a brain PET. Taken with a particular radiopharmaceutical, so F18 florbetapir, which is used to image amyloid deposition in the brain. I'm going to talk a little bit more about that in the slides to come. Next to it, you see a CT image, and then you see the two images that are fused. So say someone interpreting that image in the clinic might be able to look at both, you know, the uptake, you know, where is the amyloid being deposited, and match that essentially with structural imaging. So I'm going to be talking today in the context of a couple of projects that we've done in the area of dementia. So we have colleagues at Sunnybrook who work in dementia. A couple of background points here. So first of all, you know, dementia can start, you know, early at a form called mild cognitive impairment. A lot of people get that as they're getting older. They start complaining about, having forgotten things, but they're really not particularly impacted in their daily activities. But once you have that mild cognitive impairment, there's about 10 to 15% of the people who progress to full-blown dementia every year. Dementia is a much more serious loss of cognitive ability in the sense that it really does disrupt your daily activities. And there are various forms of dementia out there. It's estimated, although it seems like a small number to me, but that at least 50 million people have dementia worldwide. Typically, how's it diagnosed? Well, typically based on a clinical evaluation. You meet with the patient, you run a battery of tests on them. Imaging often plays a key supportive role, so that might be, not just PET, which I'm talking about today, but certainly CT and MR play a big role. So now to bring this to the world of machine learning, some of the questions that we're interested in are what can be predicted based on PET. And so some of the radiopharmaceuticals that are used in brain imaging, again, quite a few of them out there, each with sort of their own flavor of what they're trying to do. I'll start with the second bullet point, 18F-FDG. That's sort of the bread and butter of a nuclear medicine clinic. So FDG is basically a glucose analog, so think of sugar. And it's used to measure metabolic activity. And why is it the bread and butter to a nuclear medicine physician? Well, it can be used for cancer. Cancer loves sugar. It needs food. But why is it useful in dementia? Well, an active brain loves sugar, right? It needs to be fed, and a more inactive brain doesn't need as much sugar. So you can look essentially at the uptake of FDG in the brain and start figuring out what is happening. You can look at it in terms of regional analysis. So then that first bullet point, 18F-fluorobetapir, binds to amyloid, and there's a lot of stuff out there, both in the scientific literature and in the popular press these days, about amyloid accumulation in the brain and its impact on dementia. People are still trying to understand what the various processes of accumulation are, but also the impact on cognitive abilities. So 18F-fluorobetapir is one of those many radiopharmaceuticals that binds to amyloid. So again, you can image essentially the deposition of amyloid in the brain. So a lot of clinical trials right now, and there's a lot of databases that you can use, and that speaks a little bit to what Helen was talking about before, is that there are clinical trials being run across several different sites, and again, making sense of data coming in from various places can often be quite tricky. But essentially, the holy grail here, and where there's a huge opportunity, and perhaps even to monetize things for the industrial audience here, is prediction. And so in the nuclear medicine community or radiology community, you often hear people talk about machine learning just displacing them, putting radiologists basically out of work. And I don't think that's really what's going to happen. Now, they might need to adapt themselves to the new tools, but I think machine learning and AI are going to come in as good tools to aid them. And I think where things can be really helpful, it's that point in Helen's talk, what will happen next, right? Can you predict early on? You're in your 50s. Are you starting to see amyloid deposition? Is there, can you predict what that long-term prognosis is going to be? Can you personalize treatment? Can you improve treatment, and so on? And I think that's really where machine learning has a huge opportunity. And I'm going to speak about a couple of different areas in which we've applied it. And a lot of people nowadays in machine learning talk about deep learning. I mean, that's kind of like that big flavor of machine learning right now, and that imaging is readily processed using these deep learning approaches, right? It's a really nice fit with medical imaging. But I do want to also convey that much more traditional approaches are also really relevant, really insightful in this area. So the first one is actually going to be one of those more traditional areas, traditional algorithms. So we looked at using random forests. So I'll talk a little bit first about our data set and then kind of get to what our findings were. So we have a data set, and this is a multi-site trial being run across Canada, funded by CIHR, called the MITNEC trial. It's looking at many different things, but basically in our context, they're looking at patients who have either mild cognitive impairment or very early Alzheimer's disease, so not sort of late stage, and who have white matter disease. So again, think gray matter or white matter, and to a computer engineer, at least my very vague understanding in this field, I tend to think of the gray matter as being like logic gates, and white matter as being like interconnect, on a chip. So there's disease in the connections, essentially, in this population. We have access both to the 18F-fluorobutapyr PET and FDG PET studies. Our clinical partners read them as either positive or negative for amyloid deposition. We also have various other data. We know their ages and how much white matter disease and so on we have for each patient. Now, in random forests, and I'm going to talk a little quickly about them, often you're not processing the images directly. You're processing sort of features that have been extracted from the images. So we had to do pre-processing. So just a few cool pictures here of a couple of studies that we pre-processed before running it through a random forest. We've got two lines here, top one being a negative patient, not much amyloid deposition, second one being a positive. You can see from, those images bottom right, and you can probably see it from across the room, all these big red hot spots, right, represent a lot of amyloid deposition. Now, what we want to do is kind of extract, is there deposition in various parts of the brain, the precuneus, various lobes and so on. So if you start on the left-hand side, that's our raw PET. And to extract features, really what we would need to do if we're dealing with a raw PET is that the clinician would have to go in, sort of draw boundaries around various regions of interest and extract that data. But we really wanted to automate that, and so what a lot of people out there do, well, we've got the MRI taken nearly at the same time, and that PET or that MRI is used as an intermediate stage in order to essentially map, to register that PET onto a template. You see this nice clean template in the center, and on that template we've identified all of those regions, and we can extract that data. So here, again, just quickly running from left to right, the raw PET, patient's MRI template. So that's all being used to then, create this fourth image, which is the PET mapped onto that template. And then that last image on the right, we just show one of those regions that's been drawn from which we can extract numbers. So that takes us here. Not going to spend a lot of time on this slide, but basically you can see we've got 59 different regions of the brain, out of which we've extracted how much uptake of that radio tracer there was. And so that's fairly simple, can be automated, and that can go into a random forest. So a random forest basically is a collection of decision trees. So decision tree, you kind of look at one of those regions, is it bigger or is it less? And you kind of, work your way down to a decision at the bottom. What a random forest does, though, is instead of just having this one decision tree that might encode all sorts of noise, if you've got lots of data, it creates essentially many different trees, each looking at a subset of the data. I'm not going to get into too many of the technicalities here, but I've just got essentially a very quick example here in this table. Create a decision diagram here. We choose a random subset of cases. In this case, we might take these lines 1, 3, 8, and 9, and we might take 3 different features here, and we try to figure out which feature best separates the data into negative and positive. So I'm just going to quickly run through here. We could pick another random number of cases, again at random another number of cases, and create this forest of trees. So now when new data comes in, we can look at that new case against all of those trees and see what the majority decision happens to be. So in this case here, we've evaluated it against all 3 trees. 2 of them tell us, yes, it's positive. 1 of them says it's negative. Well, 2 outweighs 1, so we will call this new case positive. It tends to work very well as an algorithm, fairly simple to program as well. So, a couple of pages of code and you're basically there to give you some insight. So some insights that we learned, and I'll get into our own results in just a slide here. Fairly easy to program. Why not just 1 tree? Well, if you had 1 tree and you had, thousands and thousands and thousands of cases that you were trying to encode, you might have some branches somewhere in that tree that would have various oddball cases. So RFs are just seen out there as being really tolerant to what's called overfitting. We can also look at the root nodes of these trees and basically see, well, which ones appear more often, and that gives us insight into which of those features are perhaps more important than others. So we've used that in a couple of papers that have been published in clinical journals. So the first one, we were really just trying to see, could a random forest come up with the same clinical reading that the nuclear medicine physician had come up with. So a 10,000 tree RF, basically fairly sensitive, 86% sensitivity, 92% specificity, and 90% accuracy in predicting the clinical read and for amyloid deposition. And not only that, we also looked at what was popping up at the root nodes, which of those features. So there's some features here, I've listed them: left posterior cingulate, left middle frontal gyrus, and so on. And as it turns out, those are features, it's not a big surprise, right? But those are features that the clinicians themselves have pinpointed as being important to look at, and that do have an impact on cognitive ability. So again, that kind of gave us confidence that there was something real going on here. I just want to point out to those numbers here, because in Helen's talk, you saw some numbers of sensitivity and specificity, on the order of like 97, 98%. Here we're dealing with, first of all, the data set with 57 cases in it. So we really we see the impact of that limited size of a data set. And that's one of the negative things we have to deal with in nuclear medicine. So think about it this way: you're taking a patient, you're injecting them with a radiopharmaceutical, right? That's expensive to process. You've got to transport it. All sorts of issues, regulatory issues there. So it's not really inexpensive to gather that data. It's in fact quite expensive to get every data point. So you do tend to see a lot of papers out there that talk about data augmentation techniques and so on. So it is a bit of a limitation there. The other one is that the nuclear medicine physicians themselves will admit that if they can get an accuracy in that low 90% range, in this area, of course, they're doing very well. Second paper, we actually wanted to see, could you predict some of the cognitive function, again, based on random forests. And again, we built random forests. I didn't put down the numbers. They weren't quite as high as the numbers in that first bullet point in that first paper. But really, we were again able to pinpoint which of those regions of the brain had a very significant impact on, or normally would have an impact on cognitive abilities. So that was sort of our first foray. We also looked at other sort of more traditional algorithms. We looked at clustering, and so we just published a paper recently on k-means clustering. And again, it did surprisingly predictive of what the clinicians come up with. So now I want to move on, just quickly in the few minutes that I've got left to speak here on another area, and this one here is actually funded through the Waterloo AI Institute through the Microsoft Canada project for social good. I've talked about in PET, we are injecting a radiopharmaceutical. So for one thing, it's expensive. not every site around the world can produce it. So sometimes they're, and not everybody has a cyclotron and so on. So sometimes these need to be transported. There's notions of half-life and so on. So it's expensive for one thing. It does expose the patient to a bit of radiation. Now, it's not huge. After all, people are doing it for good and to understand what's happening in their body, but there is a certain exposure to radiation. So there's a big area of research right now that is asking whether better signal processing, and to get to the point, whether machine learning can be used in the reconstruction process for images to improve image quality such that the dose of radiopharmaceutical could be reduced, right? So you can see here the social good coming in, right? Less exposure to radiation, lower manufacturing costs, lower transportation costs. And certainly, some papers we've seen out there reducing things down to like 1% of the original dose. Possible other dimension that we are looking at as well is could we use machine learning not just to reduce the dose, but could we also reduce the scan time? So in these brain studies with 18F-fluorobutadiene, we are imaging the patients, or they are imaging the patients in 4 5-minute sequences, so over 20 minutes of time. You're basically expecting the patient to remain still during that period of time. And certainly a patient population like the one they are looking at, right, with dementia and so on, that's not necessarily easy on the patient. You get motion artifact, right, over 20 minutes of time people do move, better comfort and so on. So we're also looking at reducing that scan time. So in either way, what does that mean? Well, you're capturing essentially fewer gamma rays, essentially, which is what you're capturing, fewer counts. And so the images that come out look much grainier, much noisier than the normal images that the physician would be interpreting. And so our approach in the project, we're intending to use what are called generative adversarial networks. They're very advanced form of machine learning model, deep learning model that has basically a couple of neural networks. But what I'll show you right now is we trained a neural network that has what we call a U-net structure, and that just basically speaks to how the layers are organized. And we're trying to get it to predict what a full-time PET, full dose PET would look like based on images captured in 1/4 the amount of time. So essentially 1/4 of the counts. Oh, can you hear me again? Hello?
Yep, you're back, Vincent.
I'm back. Okay. Can you see my screen now?
Yep.
Okay, good. So here's the structure. So basically 18 layers. This isn't huge, right? And, in the context of some of the machine learning algorithms, certainly, you'll probably see during today's talk some that are much bigger than that. But just to show you, a bit of insight into our preliminary results at this point. And here I'm using a data set taken from ADNI. So that ADNI is a huge, basically, consortium of many sites across the world. In fact, interested in Alzheimer's disease. So here I show you the two images on the left. The first one is one taken over just a 5-minute sequence. The next one is the full image, right, taken over essentially 20 minutes. I call it averaged in the sense that there are 4 5-minute sequences that are then averaged together. So really, think of the image on the left as being the input into the neural network model, and the middle one as being the target, right? That's what we're training with in a supervised manner. And just showing you one image here, but we're starting to generate quite a few of what can come out of the neural network on the right-hand side. We're still at that stage. You can kind of see it's a nicer image. It's a little bit cleaner, certainly much nicer than what we see on the left-hand side. Certainly our nuclear medicine people are excited to be seeing that. We're still trying to convince ourselves at this point that it isn't just basically just giant blurring filter. So how are we going to do that? The plan again is to now do this regional analysis, a little bit like we were doing with the random forests, on these outputs and basically see, are we getting similar numbers? The other thing we intend to do, looking at this to look at the quality of our findings, is to take these outputs from the neural networks and to put them into commercial software to be interpreted. And again, are we getting similar results to what we would have had using the full dose image? So some challenges, well, data. It's kind of location in real estate, right? Data. Clinical trials, as I said, are expensive. Data sets are often quite limited in size. And if you look at things like ADNI, you're pulling data from many different sites, taken on different scanners, maybe slightly different dosages, and so on. And a lot of the tag data often has to be read by a physician. That's expensive. Okay, so certainly that data collection and data processing is important. But the next one, and I'm going to conclude on that, is and I'm looking at this more from the point of view of the clinician, is that interpreting those high-level results can be challenging. There's what I'll call inconsistent reporting across publications, and I think that's what is confusing the clinicians at this point. They go to conferences and they'll sit in a session and they'll see 7 or 8 papers, each of them touting how great the person's machine learning algorithm, their own particular flavor of it, has had an impact on their particular set of data, and there's very little of that higher level insight. If you were just getting into the field, you wanted to use it on your own data set, what approach should you take? And so here, I'm just showing you one graph here. This is really more of a thought experiment that I was trying to do in terms of how you might measure the impact of machine learning on, and I picked this area of low dose PET. So coming from the engineering world, I like to draw graphs, and especially if graphs can show me trends over time. And so in this graph here, vertical axis might be, say, the percentage of a full dose that has been injected. So 100% would be what is normally injected, and ideally we'd like to go lower and lower on the graph. Horizontal axis represents the cost of my machine learning algorithm. Again, I don't have a nice way of putting everything on that same line. It might be the flops, or it might be the number of parameters to be learned. And ideally, what I'd like to start doing is to for any paper in this area that gets published, I'd like to be able to take the results from that paper and to put it down on this graph. How successful were they? Did they achieve 95% accuracy, 90%, 80%? And I sort of posit that we'd probably see these sort of trend lines starting to emerge. And the more complex the algorithm might be more towards the right-hand side, those kind of more brownish curves. Maybe more traditional algorithms might be more towards the left. Human, it's not using machine learning, so I'm not putting the human on the left, in any derogatory sense here, but more that that they might be able to achieve a certain accuracy. And then maybe even a holy grail here is, can machine learning do such a good job processing that you might start seeing some features popping out that hadn't been seen in the full dose image. So that's just a bit of a thought experiment at this point. Certainly, I would like to engage with anybody in discussion. Not necessarily right now because we're probably short for time, but in the long run. So I'm going to conclude on that. Just acknowledge all of my colleagues. So trainees. Lewis Lee's is a master's candidate on the Microsoft project. Got a co-op student right now and a student volunteer. Key collaborators, so Catherine Zukadinsky at McMaster is my spouse, right, the nuclear medicine physician. Sandra Black at Sunnybrook is in one of the big gurus in dementia, and we've had funding, as I said, from the Microsoft Canada project, and we're getting data from ADNI and from the MIT study. So on that note, I thank you for your attention and open the floor to questions.
Okay, thanks, Vincent. We're basically out of time, but let me ask you one quick question.
Yeah.
So you presented random forests and deep learning, and so a hot topic right now is explainability. So random forests, you can sometimes generate an explanation. Deep learning, less so. How important is explainability in this setting?
Well, I think that's a really good question, and because I think explainability eventually to the physician is important, because they might have to write a clinical report, which is legally binding, right? And so the more insight that they can have as to why things are the way they are, the better. I could go on for 15, 20 minutes talking about that topic, so I might just leave it at that for now. But that's a really good question.
Right. So it's not just the yes or no, it's the report.
No, and certainly from experience, random forests, yeah, you can look, what decisions are being made, and you know why it's making the decision. Starting to see other things that sort of combine various techniques, sort of a hierarchical approach as well. So I've seen a paper recently where they basically look at that middle layer in a UNet, the feature space, they extract information there, then they put it into clustering and so on. And that's quite insightful as well.
Okay, thanks. Very interesting.